Hello and welcome, everyone. I can see that we have people from every continent attending this webinar. Encardio-rite is a 54-year-old organization with tremendous experience in the field of monitoring. The group is a world leader in monitoring and provides complete solution for sensors, data loggers, and databases. We have started a series of webinars to share our learnings with you. Today, my colleague and I shall be sharing our insights in water table monitoring with you. Manish, as you all know, is a stalwart in the industry. He has been over 25 years in the field, working on all kinds of applications. I have been associated with the industry since the last 4 years, and I've had the privilege of working on the Expo Link in Dubai. Encardio-rite is headquartered in India. We have our offices all over the world: USA, Europe, UK, Australia, and Middle East. We effectively provide our global experience at a local level. The image shows our presence on the world map. We have experience in almost every application area. Our sensors have been used to monitor over 220 kilometers of metro projects, 300 kilometers of rail and road tunnels, 160 kilometers of sewer tunnels, over 200 dams and hydro projects, over 100 high-rise, high-structure buildings, over 4,000 online groundwater monitoring level wells. In metros, our sensors are currently being used at the Grand Valley. We have over 4,000 IPI sensors and many other sensors that have been used over here. With regards to metro projects, we are also working at the Los Angeles Metro, Copenhagen, Chile, Dubai, and Doha. In terms of high-rise buildings, we are associated with the foundation of the tallest building in the world, the Burj Khalifa. Marina Bay Sands, which is the highest elevated swimming pool. Also One Zabil, the highest link bridge in the world. The deepest shaft at 110 meters for a pump station, the highest railroad, the highest arc bridge for a railway are some of the incredible projects that we have been associated with over the past few years. We have worked with some of the best designers, consultants, contractors, and stakeholders in our field. While the webinar is going to focus on water level monitoring, we have experience in monitoring both water level as well as pressure. In almost every construction project and existing structure, the role of monitoring the water pressure is very critical. The fort that you can see in the slide is in Oman. Originally built by the Portuguese, the fort is surrounded by water. The surrounding saline conditions and numerous rainwater discharge points had caused adverse weathering and erosion with time. An intensive slope stabilization and monitoring plan was implemented. More details can be found on our website at encardio.com. The same sensor that we use for water level monitoring can also be used for monitoring water pressure too. In case we need to measure water pressure, the sensors can be installed at multiple locations in the borehole, connected to a single data logger, and go through GSM, where data can be transmitted to from our laptop. This slide shows us an image of a multi-level piezometer installed at 5 different levels in a borehole. This was installed in the largest and deepest pump station in the world. You can see that the deepest pump station, the deepest piezometer installed here is at 127 meters. The graph represents change in pressure at different levels. Our sensors are world class. India has great expertise in manufacturing. You all must have read that iPhones are being manufactured in India. Encardio-rite is the only company in this field that provides the complete in-house solutions. We manufacture our advanced data loggers, sensors, and have our own proprietary database. We are the only company in the geotechnical space to sell sensors that are electron beam welded, ensuring that the sensors work endlessly. Few of our sensors have been providing data for over 25 to 30 years. One of the other big advantages of our sensors is that we can supply them without cable if need be. The cable then can be joined on site once the exact length of the cable is determined. We all know the one reason for failure of sensors can be bad cable jointing. With this unique technology, the risk of bad cable joints is dispensed away with. On the right, you can see an image of our electron beam welding machine used for welding our sensors. Coming to our data logger, Encardio-rite has the most advanced digital data logger. It is a compact, brick-sized box. Our digital data loggers come with two-way communication. You can sit in the comfort of your office and reconfigure the system or set alarm values. There are four ways of data transmission. The data can be transmitted to a remote server using GSM GPRS modem or radio frequency, or alternatively, you can download the data via Bluetooth on your mobile phone or using a serial port on your laptop. We also provide multi-channel data loggers, which can be used for multi-level piezometers. The power supply is versatile. The data loggers can be operated through a 12-volt power supply output, battery, or even solar panels. Battery life on our data loggers lasts up to 4 to 5 years, keeping in mind that we acquire 4 readings a day and transmit that data once a day. In our systems, we have done away with the vent tube, resulting in a complete sealed sensor. The vent tube had two disadvantages. They used to get clogged, as well as the desiccant needed to be changed frequently. The need of a vent tube was to compensate for the effect of atmospheric pressure on water level. By adding a barometric pressure sensor, the need for a vent tube was dispensed right away, giving it an almost maintenance and hassle-free system. The most important groundwater parameter measured is water level or water table. However, for proper monitoring of groundwater resources, online web-based monitoring of the following parameters is also necessary: water temperature, water conductivity, water flow or discharge, and rainfall. Our system has the capability of integrating all these in our sensors. As we know, around 3% of water on Earth is fresh water. About 69% of this is locked up in glaciers and ice caps. 30% is found as groundwater, and 1% is accounted for in lakes, rivers, reservoirs, or the atmosphere. Groundwater is one of the most important sources of fresh water. It is fast disappearing. Groundwater has therefore to be judicially used and also recharged. The data shown on the groundwater at this location has depleted by almost 8 meters in the past 6 years. For monitoring the effectiveness of these plans for reduction in water consumption, conservation and regeneration of water resources, it is essential to comprehensively map, measure, and monitor the extent of both subsoil aquifers and surface freshwater reservoirs, as well as to recharge them during rainfall. There are a number of factors that impact the correct monitoring of water level. The next few slides will explain about these factors and how they can be mitigated. For water with dissolved solids, the specific gravity of water of that location has to be separately determined, and the correction factor has to be applied to the measured value to determine the water level. Brackish water in coastal areas often has a specific gravity as high as 1.1 and therefore requires a specific gravity correction to be measured to the measured value. This correction can easily be done in our data loggers using the below formula on your screen. This graph shows you an image with the effect of atmospheric pressure. On the left-hand side, you can see groundwater level in meters in blue, and the right-hand side shows you barometric pressure in red. This graph is a graph which shows you the change in the effect of atmospheric pressure over the past year. On an annual basis, variations may go up to even 300 mm water column level, or even up to 500 mm water column level on several areas which can be seen due to atmospheric pressure. This graph here shows you a weekly variation of atmospheric pressure. It has been seen that even on a weekly basis, atmospheric pressure can vary up to 200 mm water column level. One can therefore imagine the kind of change and impact it has on the accuracy of monitored water tables. Changes in atmospheric or barometric pressure can cause groundwater levels to fluctuate. This is affected by barometric pressure change as the capillary opens into the atmosphere. Atmospheric pressure is caused by the Earth's gravitational attraction of air in the atmosphere. The relationship between water level and atmospheric pressure is an inverse one. An increase in the atmospheric pressure will cause the water level in the well to fall, and a decrease will cause the water level to rise. The output of water pressure sensors is also affected to some degree by the change in temperature of the water surrounding the pressure sensor. This behavior is called temperature drift. However, for groundwater monitoring applications, the temperature drift is not much relevant, as for groundwater of a depth of more than 10 meters, the change in temperature is typically to be found less than 1 degree centigrade change for the entire year. I will now ask my colleague Manish, who is going to take us through to the case studies as well as give us an online monitoring view.
Hello, everyone. Hope you must have found details shared by my colleague Rushil interesting and informative. In this particular part of session, we will share on selection on range of sensors, few case studies, data management software features, and live demo on the online system. Continuing on water level measuring system, we now address an important aspect on selection on range of sensors. When you are referring to any requirement specifications of water level recorder, it would generally state as a digital water level recorder, non-vented type, having a measuring range of 0 to 120 meter with sensor cable and suitable for a borehole depth of 120 meter, along with accessories like junction box, cables, battery operated data logger, telemetry system based on GSM GPRS, complete as per the technical specifications. If you see here, it says that the range of the sensor has to be 120 meter as well as the depth of the bore well also is 120 meter. The measuring range of sensor should be based on the actual depth of installation of sensor and not on the deepest point of the borehole in which it is supposed to be installed. The actual depth of installation of sensor should be based on the maximum change in water level expected, and it may not be the deepest point of the borehole in most of the cases. Using a sensor of high range based on borehole depth than what is required will compromise the accuracy of the readings. Let's have an example. The maximum drawdown expected in a borehole of a 100-meter depth is 15 meters. Accuracy considered is plus and minus 0.1% of the full scale, which is a full scale range. In that case, selecting a 1 megapascal range piezometer based on the borehole depth will result in an inaccuracy of plus and minus 100 millimeter of water column, which is 5 times worse than the inaccuracy of plus and minus 20 millimeter, which one have got using 0.2 megapascal range piezometer, actually suitable for the application. If you see the table on your right, row 5, depth of construction is mentioned as 111.6 meters. Water level pre-monsoon is 3.8. Water level post-monsoon is 3. Tentative depth of installation of DWLR is 8.8. We can right away select a measuring range of 0.2 megapascal range piezometer and achieve a good accuracy. Moving on to some of the case studies prepared on evaluating data from the installed automatic water level recorder with respect to site condition and its behavior. Let's start with rainfall. An important parameter is monitoring of rainfall that affects water level in the ground, rivers, and lakes. It provides valuable information on correlation between rainfall and magnitude of percolation of rainwater into aquifer over a period of time. Here you can see that because the discharge is very high, despite rainfall, the aquifer does not get recharged. On the left side, what you can see here is the chart on water table, and on the right you can see is the chart on rainfall. And the bottom here, what we see is the period, the duration. This graph shows the data from 1st of January 2014 till 11th August 2020. Here you can see that the discharge is very high. Despite rainfall, the aquifer does not get recharged. And in 2018, rainwater harvesting was started at this site. The immediate effect can be seen by this data. The water table went up by 1 meter post monsoon season. The other interesting fact to note is that aquifer may not get recharged immediately after the monsoon. However, it will depend on number of factors. Generally, water seeping down in the unsaturated zone moves very slowly. Assuming a typical depth to water table of 10 to 20 meters, the seepage time could be a matter of minutes in the case of coarse boulder, to months or even years if there is a lot of clay in fine sediment. Under saturated conditions, the water might move a lot faster. Other factors include the configuration of the wetting front, the unsaturated storage, temperature, and the hydraulic gradient. It's all a matter of the local hydrogeology. In the graph, it is clearly visible that the location witnessed the maximum rainfall in July. However, the recharge of the aquifer was only evident a month later. Good recharge at a higher water table. In one of the region areas with higher water table shows a different trend in water level variation. It was observed that the water table reached to its original level after each monsoon. Groundwater table variation and water temperature from two different locations with higher water table are shared here. For this particular site, the data is shown for a period of 2 years, and this particular site, the data is for a period for 3 years. A rise in water level is seen prominently with the advent of rains at both these locations. It shows that the rainwater recharges the subsoil aquifers and recovers the water table completely in this region. This implies that the recharge is better at higher water table. Daily change in the water table. The hydrograph gives data from an automatic water level recorder installed in one of the region. In this particular chart, we are seeing the data recorded for a period of 3 months. And the next chart, we are seeing the data recorded for a period of 3 days. Both the data are of the same borehole. The data was recorded 4 times in a day and transmitted once in a day. From the hydrographs, it is interesting to observe the daily variation in water level during day and night. The water level goes down in day by around 3 to 5 meters due to high consumption and recovers at night. This gives important information about the aquifer in that region. The fact came to light only after the installation of the DWLR, because earlier the data was taken only once in a month. Pumping of the water. The online data from an automatic water level recorder installed in one of the farmhouse gave interesting information. This observation well is very near to active water wells used for pumping groundwater. The rapid water level fluctuations recorded are due to the pump cycling on and off. You can see here there is a water fluctuation, and this is all because of the pumping of the pumping cycling on and off at the nearby producing well. The water went down by almost 7 meters during pumping. However, this level was back to original within 2 to 3 hours. Both these factors can be seen clearly from the slide, which is for the 7th day and as well as on the 3rd day. Interestingly, if you see the next slide, the 15 months data, we observe that the bore well discharged slowly or negligible at higher levels. Also, the refilling was faster and instantly. This may happen due to some aquifer or soil layer at deeper depth that slowed down the refilling. This also shows the probability that the bore well in which the system was installed was not giving the water table of that area, but the water level in that particular well. The other interesting observation from this data is that water temperature at this depth remain almost constant. Even if you see the first slide of 3 days data, the temperature shows is 28 degree. On the 7th day, also the temperature, the red one, and here you can also see the temperature, it shows 28 degree. The same borehole after 15 months, we can see the temperature still is close to 28 degree. Now we come to the presentation and reporting of the data. Data is normally presented as pore water pressure versus time, drawdown versus time, groundwater level versus time. The graph here shows change of water pressure against time in deep and shallow piezometer installed at one of the underground projects. The height of water head above the sensor tip measured using a water level sounder has been converted into a pressure. The values displayed here are all in kPa. So the value of the water level has been converted into pressure. And this is the duration. This is the time frame. 1 meter of water column equals to approximately 1 kilopascal. And here we are trying to show the change in water table or water pressure from two different boreholes or two different piezometers. One is at the deep location, the other one is the shallow. The one what you see is blue is with the deep location, and the one what you see with the red kind of a thing is with the shallow. The graph in this slide shows the change in drawdown with time in the observation well installed outside the excavation area of one of the underground project instrumented by us. It also shows the variation of water level. That is the one which was recorded before the start of the dewatering activities with time. On your right, you will see number of manual and automatic piezometer installs. The alert and maximum allowable levels are also shown for a quick evaluation of the situation. If the user has programmed sensor with triggering values in above, it is alert and maximum allowable. The yellow line that you see here is for towards alert, and the red, what you see is a maximum allowable limit. Otherwise, the user can also program it to be for alert, alarm, and action, the three parameters for the AAA values. The moment value reaches any of the alert mode, user will receive an SMS or an email alerts on his or her device. Sometimes it is useful to put additional data series with the graphs on the secondary y-axis, such as excavation level, the distance of excavated phase, with reference to the piezometer location, barometric pressure, temperature, dewatering discharge, etc. The choice of second parameter depends on the application. The graph here shows the groundwater elevation on the primary y-axis and the dewatering discharge on the secondary y-axis. This allows an easy visualization of the correlation between the two parameters. We can see groundwater elevation going down as the discharge rate goes up. Here are two piezometers. Here the water level is going down. As we can see, there is a high discharge being shown. So we can have a better correlation if we have two different parameters on y-axis, and we can have a better comparison when it's for the drawing down. We come to Encardio-rite data management system. It's a versatile and can correlate data from hydrology, geotechnical, structural, environmental, etc. We offer a complete online cloud-based or a local access data monitoring solution for monitoring water resources or civil engineering construction projects. The salient features for the software: easy access to meaningful instrumentation data. Data is presented in graphical as well as numerical formats. Results are accessible on tablets and smartphones. Access to different sensors on one screen. Combined charts in one report. You can have number of combinations. Create diagrams from any combination of parameters and time period. Multiple authorized users at different locations can simultaneously interact with the software to view any real-time data, changes, graphs, or reports. instant alerts via SMS or email to authorized personnel, low operational cost, and user-friendly tools for day-to-day operation. Let's go online with this particular link. This is our web page portal. We need to put the username for the project as well as the password will be allotted, and then we just log in. We can have any kind of information, like we can have the project images, we can have JPG files, we can upload the drawings, and we can mark the instrumentation on those particular pictures. We select one of the location where we want to actually see the change in water levels. This is how the web page looks like. On the left, you can have your indexing for the different parameters to be viewed. You can see we have categorized into landslide, structural health monitoring, and for water. And in water, we have segmented into change in water level, depth of water level, barometric pressure, rainfall. So let's start with water level. What you see here in blue is the water level, the current water level, and what you see is the temperature. Here you can see the maximum, average, and the minimum values for a period of 1 week. The period is 5th August till 12th of August. This is the temperature bar. This is the change in water level or the water level bar. Let's change the resolution. Here we have a scale. We can always configure. We can play with this. Currently, it is set for 1 week. I'll change it to 1 month. You can see the data from 13th of July till 12th of August. You can see the water level again. The temperature is constant throughout. You can also see the average for the whole month. The software also has a feature that you can see the tabular format, the numerical values of those graphs. You can see the data from 13th of July, water level, the temperature, and you can come down and you can have the data from your selection point. Coming back to graphical value, let's change the scale. Let's go 8 years back. We'll go in 2012. And let's take the current period. Interesting figure. The water has been depleting right from the beginning of 1st March 12 till date. You can see here, if you take the average, the maximum was minus 34.51 and the minimum was minus 43.08, and almost kind of a drop of 9 meters in last 8 years. And temperature, if you see, has been a kind of a constant between 25 and 26. Let's take rainfall along with this for the same duration. You can see this. This is water level, the drop in water level, and these are all the different years of the rainfall in that particular region. Let's click on this. You can see there's only a steep rise here, but rest all the water is been dropping down. Even you have a feature of either saving the data, or you can print it, or you can save the PDF file, or you can email to any, at any given point, whatever period that you select, you can have everything available at a touch of a button. Let's take barometric pressure. Here is a scale again for last 80 years. You can see the same water level, but you can also see the change in barometric pressure. The bottom slide also is of the same period. The only thing is we have changed the scale of barometric pressure. Here you can see it's from 900 to 1100. Here we have changed the scale from 970 to 1030. That's why you can see a larger amplitude or the larger change here in the barometric pressure. So that is all from us right now. Thank you all for attending the session and spending your time with us. You may please raise your questions and we would be happy to address them.